it's easier if it's broke. So what I'm going to cover, what I want to cover is the shared memory model in MPI, which allows you to have shared data structures like arrays across a node. However, to do that, you need to understand the basics of the original remote memory access model, which didn't allow you direct read and write access, but required you to use function calls like MPI put and MPI get. So I'm going to have to cover that. So I'll go through this relatively quickly and only pick out the same. This talk goes through the whole of all of those issues, and that's not really, we're not really interested in that. But I will just find the sorry about this. This is gonna. Sorry, because because I'm on a different laptop. Okay, so I need just to find the. Apologies about this. Oh, there it is. Sorry. Okay, so if I share this correct slide, sorry for the delay. Fine, okay, I got there in the end, sorry about that. So this will introduce the concepts of remote memory access, and I'll concentrate on the bits which are interesting for us, but it's worth understanding where it comes from. So this is the original model for remote memory access in MPI, allowing you to read from and write to another process's memory without there being a matching send or receive. So a write is like a send without a receive, and a read is like a receive without a send. So, why are people interested in RMA? What is the terminology? How do you write your program? And then I'll talk about management of windows, event synchronization, moving data around. And we're not going to do this practical. We're going to do a different practical. So what are the RMA concepts? Well, this is the basic idea that it's sometimes called a single-sided model of remote memory access. It's called single-sided because in MPI is a two-sided model with send and receive. In the RMA model, remote memory access, only one process makes the call. So the remote process does not actively participate. So for example, the origin process could write into the remote process's memory. Now there are two issues here, or the number of issues, but the first issue is where can this origin process write to? Well, in RMA, MPI introduced a new concept called a window. And what you do is you say here, or you collectively agree on areas of memory which can be remotely accessed. So that provides safety. You can't read from and write to a random area of another process's memory. It's only a piece of memory which that process has said, I allow you to do remote memory access to this region of memory, which would typically be an array. Synchronization is now a major issue because, like any model where you don't have matching send and receive, if you read data, you wonder if it's valid. That is not a question when you do it. When you do a receive, the send is only issued when the data is ready to be sent. So, and also if you do a send, the remote process only receives it when it issues the receive. So you never send out of date or receive out of date data. However, if you directly read and write, you're always worrying that you're scrubbing over memory or you're reading data which isn't correct. So synchronization is a major issue. The motivations why extend the basic message passing model? Well, quite early on in message passing, when people were writing MPI programs, they were writing sends and receives. They said, well, actually, I know how this network works at a very low level. And I know that the network allows for remote memory access in hardware. I know that the network allows me to read and write directly to another process's memory. Of course, this is the fundamental model for a shared memory machine. And so people started to use these low-level RMA calls for efficiency. because they felt they got better performance than MPI, and this led to the development of non-portable parallel applications. So that's the hardware reason. The software reason is that many algorithms are naturally single-sided. It's very often the case, I don't know if you've done some sparse matrix vector multiplication, it's very often the case that I'm a process, I know exactly where I want my data to go to. But to achieve that, I have to do two things. I have to tell those processes to issue a receive, then send them the data. Now, if you have a static communications pattern, that's just a hassle. At program startup, you do a big shuffling around and you tell. But if the communication structure changes, every time the communication structure changes, I have to basically tell everyone who should issue a receive to me, and then I send them the data. Would it not be much easier if I could just say, I want to send data to processes 7, 9, 53, and 27, and just write into their memory? They don't have to issue the matching receive. And so this is a real issue if you have like an adaptive decomposition where your program structure changes as it runs. So why RMA? So these one-sided communication function interface to the MPI remote memory access. Basically, one-sided is a confusing term. It may be the data transfer is one-sided, that only one side issues what we call a put to write data or a get to read data. But actually, the synchronization requires participation from both sides. So, however, this is a natural fit for some codes, as I said. In some cases, it's natural. It may provide a performance scalability increase for your codes, but it's not a silver bullet. In practice, because of the overheads of the MPI library being very portable and robust, in practice with this version of RMA, where you use puts and gets, typically people don't see a performance increase, which is why they extended it, which I'm going to cover in the next lecture. But we need to know some basic concepts. So the terminology, now, when you're doing send receive, it's clear that the person doing the send has the data, and the data ends up on the person doing the receive. So the sender sends the data to the receiver. However, depending on if you're doing a remote read or a remote write, the data transfer can go two ways. So we need two terminologies. We need origin, is the process initiating the request, and target is the process whose memory is accessed. Okay. So so by the origin. So basically, all remote, so you have an origin and a target. Okay. So origin is the process initiating the request, the target is the process whose memory is accessed, and for a put, the data goes from the origin to the target, but for a get, the data goes from the target to the origin. Okay, so that's you need these extra terminologies. All remote access is performed on windows of memory for safety. The other thing is all accesses are non-blocking. The terminology gets very confusing. But technically, MPI has this idea of an access epoch. It gets very simple examples. You don't need to understand this terminology, and in fact, it was so confusing that a lot of it wasn't really very well defined. But the important point is you have to remote accesses are performed on windows of memory. So three concepts are origin, process initiating the request, target, process whose memory is accessed, and windows of memory which you're allowed to perform these remote operations on. So what you do is you collectively initialize a window, you start an RME epoch. That means you have some synchronization, which means it's safe to do communication. You issue lots of communication calls, which, as I said, are non-blocking, and you stop an RME epoch, which finishes all these calls, and then you free the window. So you have your communications, which are through puts and gets here, are delineated by synchronization calls. So you shouldn't start that till everyone's ready, and you only know the communications are finished after the final synchronization. So getting started, window creation is a collective call issued by all the processes. So what you say is MPI window create. So what you've done is you've allocated some memory, either through allocate in Fortran or malloc in C, and you say, well, actually, I don't want to do sends and receives to this data. I want to access it through puts and gets, direct reads and writes. So you give it the address, you tell MPI what the address is, how big it is in terms of bytes, and you get back a window. It's collective over communicating, you get back a window. The weird thing is the displacement unit. This is to provide you with some level of portability. At least in C, a pointed, this is just an array of bytes. The displacement units, so what we're going to do is we're going to say, I want to write to location 3 in this window. 3 watts, well, that's the displacement unit. So if you say displacement unit equals 4, then writing to location 3 will be memory address 12. It's the size of the basic object. So for example, if it's an array of integers, the displacement unit would be 4. If it's an array of doubles, the displacement unit would be 8. If it's an array of characters, the displacement unit would be 1. It's allow you to not talk about bytes in subsequent calls. You can treat it like a normal array. There's lots of room, there's lots of technicalities to do with performance and such like, but basically that's the base. That's how you create a window. You malloc or allocate the memory, and then you tell MPI to create a window, which then allows it to be remotely accessed by other processes. There's various ways to retrieve attributes, but not, and you can free a window at the end. It's fine. So the simplest way to start and finish a region of remote memory access is to use a fence. Okay? So a fence is a fence is like a barrier, okay? But a fence does 2 things. So what you can do is you call MPI win fence on a window. Sorry, I've lost my. Okay, you call MPI win fence on a window. There are various assertions we'll come back to, but you can just say 0. So basically, it's like a barrier. You do an MP. It's like doing an MPI barrier where everyone waits. You do lots of puts and gets, lots of reads and writes, and then you do a barrier at the end. But a win fence is more than a barrier. It's not just a barrier in time. It also completes. Oh, there's a typo there. There should be a capital W. It also completes all the outstanding RMA calls. So it does 2 things. It's like a barrier. It's like a barrier synchronization in time, but it also ensures that all the outstanding communications have completed. So you can't start RMA until the first fence, and all the issue communication blocks there until after the second fence. It's guaranteed that all the communications have finished. And by default, there's no assertions, but you can, and the kind of assertions you can do. Now, there's a lot of overhead in MPI to doing these things. So it's very useful to give, if you're worried about, you can just say 0 if you want, but if you're worried about performance, you should really tell MPI as much as possible. So for example, you could say MPI no proceed, okay? You might say that there have been, so when you issue the first fence, what MPI is going to do by default is to say, I need to complete all the outstanding RMA operations. Maybe you know there aren't any, so you say MPI mode no proceed. There are no outstanding. Or at the end, fence does not start. I mean, you could say that there are only remote reads or only remote writes. So for performance, the more information you tell MPI, the better. But for simplicity, we'll not look at that in this lecture. But if you're interested about performance, you'll need to look up the manual to find out which of these can help you. So having within that what MPI calls the exposure epoch, between these 2 fences, you can get data or you can put data. So to get data, it's MPI get. It's a bit like a receive. It's a bit like a send receive. You say where you want it to go locally. This is your receive. It's like a receive buffer, receive count, receive type. Target rank is the source. And if you're just doing a receive, you do buffer, count, data type, source. But remember, and that would rely on a matching send. Remember that all the parameters are specified in this. So you not only just say where the data is going to, you also say where it's coming from. So you say it's coming from, a target displacement, a target count, a target data type in this window. So these parameters are expressed are interpreted at the origin, but this is saying I want to read so many data items from the remote process at some particular displacement into the window of a certain data type, and it all happens within a window. A put is exactly the same parameters, but the data goes the other way. So here the data comes from here into here. Here the data starts off here and ends up there. So it is actually the same prototype, identical, but the data goes in a different direction. You sometimes would like to update the remote memory. You would like to say, for example, increment a shared counter. You can't do get, add one, and put because that's not safe. Something might have happened in between. So there is an accumulate, which is basically like it's like a put, but you specify an MPI op, which might be MPI sum, which says don't overwrite the data, add to it, and that's done in a safe and atomic way. But I'm not going to dwell on these because we're not actually going to use these functions. I'm really interested in showing you how windows are created and what they're used for. So these RMA communication calls are similar to non-blocking. You have to wait for synchronization, but you don't synchronize with MPI wait or MPI wait all. The subsequent fence does all that synchronization for you. And there are a bunch of technical restrictions, which I'm not going to go into. So a generic simple approach is to declare the local storage in each rank, make that storage into a window with MPI win create, and you'll notice that these put and get don't have a communicator argument, which is unusual for a communication routine. They take a window argument. So the window replaces the communicator in these RMA calls. Access data, you can just use the local arrays in normal ways, but whenever you want to communicate, you synchronize with the MPI win fence, you do MPI gets and MPI puts, and then you synchronize where everyone is finished, and then you go back to accessing the data in local storage as normal. So there is an example here, which I'll go through. It's slightly, but basically what we're going to do is we're going to issue, basically, this comes from a course in Cornell. We're basically going to do a broadcast, but we're going to do it in a slightly crazy way. Well, a way to illustrate it, we are going to have every rank except for 0 get the data. So the data will be initialized on rank 0, and all the other ranks will read it with an MPI get. So we have a master buff of size 20, which is on the master. Everyone has their own buff here. So if I'm rank 0, we all create the window, MPI win create, but the only actual valid entry is master buff. So it's master buff, it's 80 bytes long, and the displacement unit is the size of the int, which is 4. All the other ranks contribute no memory, but they still get hold of the window. So this window only has data that's valid on rank 0. We then initialize the master buffer. We then have an MPI win fence. We need that because otherwise we need it for a number of reasons, but the main reason here is we don't want the non-zero ranks to get the data before it's initialized. There needs to be a synchronization here. You wouldn't need that in MPI because rank 0 would have to actually actively send the data. Start a synchronization. If rank is not equal to 0, we will get my buff, which is 20 integers from rank 0, starting at displacement 0, 20 integers in win. And then we finish it, and then we're finished. So, that's the kind of, obviously this is much more complicated than doing a broadcast, so you wouldn't do it in this way, but it illustrates the point of synchronization and direct read and write. So you'll notice here that no communication calls are issued by rank 0. All the communication calls happen on the other ranks, and they directly read the data with a get. So the model is quite simple in principle. The syntax can be quite challenging. The performance may not be very good because the MPI is very safe and conservative. And one of the reasons you want to do remote memory access is for low latency. But all the additional software checks which MPI has to put in place mean that latency may not be very good. However, the reason I've gone through this lecture and explained the basics of RMA calls such as put and get is really the windows. The concept of a window are the key component of MPI shared memory. And the problem with this approach is you can have two processes on the same node which have a shared memory window, but they cannot directly read and write to it. only way they can access it is doing puts and gets, which is very, very inefficient. You're doing a function call to read and write a single byte. What you'd like to do is to create a window, but not have to access it with put and get, be able to directly read and write to it and read from it, at least for those processes that share a node. So that's what I'm going to cover in the next lecture. So I think it's probably best I'll take any questions now, but if there aren't, let's have a 5-minute break, and I'll start the next lecture at 2:30 p.m., which is the last lecture. I think we need a little break here because that's quite a dense lecture. Time to take a back seat, and I will. What I'm going to do now is give this final lecture, which is so this might seem slightly esoteric, but it can be a really quick win in MPI programs to do this. And this is this shared memory on a node in an MPI program. So I'll just grab the so let's share the correct window. So we're going to talk about MPI shared memory model, which as I've given here is, it's quite a delay on this. There we are. MPI processes behaving as threads. So, oops, I'm in the wrong window. So what the motivation is, okay, I've seen this diagram before. In OpenMP parallelization, all threads access to shared arrays. Why can't we do this MPI processes? Well, you actually can, because you can, if you know low-level stuff, create things like shared memory segments, but that's very low level. People started to do that, and I guess they thought, well, people are doing this to allow multiple MPI processes on a node to share the same data. Let's standardize it in MPI rather than people writing non-portable system-specific code. So this is one of my consequences of MPI plus OpenMP. I've talked about this before, but basically the main problem is that when you switch from MPI to OpenMP, you've gone back to effectively a serial code on a node. You're only using one process per node, and as you go through time over the weeks and months, you add in more OpenMP to make more of the code parallel. But do you ever regain the pure MPI performance? And if you want to do something as simple as just having a shared array between processes, this really seems like overkill. So the other use cases are saving memory. Okay, some programs have large static lookup tables. In MPI, need 1 copy per process. Much more efficient to have 1 copy per node. This is something of a technicality, which is it's a bit of a corner case. I cover this in the more detailed study I do on our MSc course. But I think for here, it's something of a corner case. But this is really the major motivating factor. Large static lookup tables, 1 copy per node, not 128 copies on each node. So how do we exploit RMA? Well, with standard RMA, we publish local memory in a collective shared window, MPI win create. We do reads and writes with puts and gets, and we do appropriate synchronization with MPI win fence. It seems wasteful on a node. Why can't all processes just read in directly as an OpenMP? So there is a technicality here. It's really a kind of an in-principle thing. But what you want to be able to do is you want to be able to basically read and write directly to the remote memory. You can imagine an architecture kind of machine where when you when you did the puts and gets, you weren't actually writing to the memory, you were writing some intermediate memory, and it was only flushed into the user's memory when you did the synchronization. So that is almost never true. But MPI defines 2 models. One is the unified model, where when you do an RMA call or put or get, it really goes into the local memory. The other one is the non-unified model. I should know what that's called actually, where there's some intermediate storage, where there's some copying going on. So technically, when you create a window, you should check whether it is this. However, I've never come across an architecture where this is a restriction, so I wouldn't really worry about this in practice. It's more of a technicality. So the procedure, first of all, clearly you can only read and write directly to a shared array if two processes are on the same node. So we're going to want to create node local communicators. We're going to all the processes on a node, 128 on an ARCHER2, to become members of their own communicator. And there's an easy way to do that now. Having done that, okay, there's this new shared array allocation routine across all processes on a node. The nodes get together and say want to do equivalent of a malloc or an allocate, but it's going to be a shared allocate. And what happens is each process receives a local array. I'll show this in a diagram, but the operating system arranges for them to be, basically each process gets a subsection of a big global array. Okay? And that's possibly better illustrated with a diagram. And so what you have is you have a little local array, but it's actually part of a bigger array, all in the same shared memory. How do you access somebody else's memory? Well, it might seem a bit naughty, but you can actually over-index or under-index the array. So normally if you under-index array, it's meaningless. But if you go local array -1 instead of local array 0, this is in C, that actually becomes the last entry on the previous process. So actually just by over and under indexing, you can allocate memory from other processes. You still need appropriate synchronization, and you still need MPI calls for internode communication. So this only works within a node. For the internode communication going over the network, you still need to do MPI, standard sends and receives. You could do puts and gets if you were brave, but I think that's overkill. So how do we split the communicator? Well, there's this routine called MPI com split type. It says create subcommunicators for all the processes based on a particular type. So you say MPI com split type, you give the original communicator, probably MPI com world, you give it a split type, and we're going to use MPI com type shared. So that says put all the processes which are in the same shared memory location, i.e. live on the same node, into the same communicator. You give it some info, but we're just going to say MPI info null. I'm not going to bother about that. And you get back a new communicator, which I will typically call com node. Now, the question might be, okay, all the processes that are on the same node are in the same communicator, but how are they allocated? What's their ordering in that communicator? That's specified by the key. And the simplest thing is just to specify the key as your global rank. And then that means that the ordering in the new communicator is the same as the ordering in the old communicator. That's the natural thing to do. So the typical thing to do would be MPI com split type, MPI com world, MPI com type shared, rank, MPI info null, and then get back the new communicator, which I typically call com node. So example, if we had com world size equals 12, and we were running on 12 processes, but it was physically 2 nodes, each of 6 processes, we do MPI com split type, MPI com world, MPI com type shared, rank, where this is your ranking com world, MPI info null, node com for these guys. So node com is of size 6, and within node com, these guys have ranks 0, 1, 2, 3, 4, 5, which is the same as their global rank. But in this guy, they still have rank 0, 1, 2, 3, 4, 5, which is different from their global rank. In a new communicator, you have a new rank. So your rank is guaranteed to be between 0 and 5 because node com is size 6. And by specifying the key as rank, the ordering is the same. So they're ordered in the same way as they were in MPI com world. So this is a nice. Now, you might say you've got a split type. What other split types are there? Well, at the moment, I understand only MPI com type. So they have the general routine MPI com split type, but there's only one type supported. But you can imagine in the future, you might say MPI com type GPU. Give me a communicator which contains all the processes which have GPUs, for example. So this is extensible, but at the moment, I've only ever used it for this grouping together processes that are on the same node into their own communicator, which I call node com. The next thing is allocating the array. Well, this array, for a normal window, you allocate the array using C or Fortran, and then you add it to the window. This array is going to have to be allocated specially. When I say what's actually going to happen is you're going to get a local portion of a global array. So the operating system is going to have to do something special to make sure they all line up. So in this model, MPI when allocate shared actually doesn't just create the window, it also allocates the memory. So you say how big it is, what the displacement unit is. These are the same as for a normal window, and you get back the base pointer. This is like a malloc, okay? The malloc would just be you get back the base pointer with size, but here you have you specify the displacement unit and you get back a window as well. So you do MPI when allocate size, disp unit, info, com, base pointer, win, IRA. Again, info is just extra information. We can use MPI info null. The size of the window is size in bytes. The disp unit is the basic counting units, which might be size of int if we're using integers. The com is the parent com. That has to be, this is collective across all the processes. It can only work if all those processes are in the same node. This communicator has to be, all these processes in this communicator have to be on the same node. Otherwise you'll get an error. And you get back the base pointer. You also get back a window. So you can now you could use this as a normal window with put and get, but you actually get back this base pointer, which you can use as if it were just a normal array. So the traffic model example, what I'm going to do here, I'm going to in the example I distributed, we communicated data with our neighbors doing send receive. Here we're going to communicate with our neighbors on the node by just over and under indexing an array. If I want to read the data from my next rank up and they're on the same node, I just read off the end of my array and into their array. So we have the same thing as before, old road, but now we have a node win size and displacement unit. So how big, so I don't allocate the array anymore. I don't malloc it or allocate it. I use MPI when allocate shared. What's the win size? This is in bytes, unfortunately. It's n local plus 2 times size of int. I'm still putting halos on these arrays just for consistency. The displacement is the size of int. So I do MPI when allocate shared. Win size, which is how much data I want. Displacement unit is 4 bytes. Info null, I get back node com. I put in node com, and I get back the old road and a window. So this allocates the storage for the old road of size n local plus 2 integers and gives me back a window as well. So imagine we did that, okay? If n local were 2, this is a tiny road. If n local is 2, then we're creating a window with 4 integers in it. So node rank 1, for example, has an array of 4 integers. So it would call this, if I call it, this would be x0, x1, x2, and x3, okay? Node rank 2 has x0, x1, x2, x3. So each rank gets a little array of length 4, which it thinks of as being x0, x1, x2, and x3. However, if you over-under index, like this guy does, x minus 1 is the last entry on rank 0, x4 is the first entry on rank 2, even x7, that's 4, 5, 6, that's wrong. That's 3, sorry, that's 4, 5, 6, 7. So node rank 2 thinks that's x3, node rank 1 thinks it's x7. So the default is a contiguous block of memory across processes. You can relax that, but I don't see the use for that. Okay, so that's what you do. It's deceptively simple. You have a special array allocation routine where everyone says they want to allocate 4 integers, but the operating system makes sure that they're all actually a subsection of a large contiguous array, and then you can do this trick of over-indexing or under-indexing. So, you know, in the previous diagram, rank 1 can access rank 2's x0 by referencing its own x4. You might say, I don't want to do that. I'd like to basically everyone have this pointer here, x0, from node. So you might think, well, let's just get node rank 0 to send this pointer to everybody. It doesn't work because of technicalities of the way that the Unix, the operating system memory management works. So again, it's a slight technicality, but if you want everyone to have a pointer which starts here, not here, you have to use a funny routine called MPI when shared query. So I've explained it a bit here, but basically, if you want everyone to have a pointer which is actually from a different rank, if you want to get the pointer from a different rank, they can't send it to you. You have to do this MPI when shared query. It says, give me the pointer, give me that ranks pointer, not mine. It's slightly a technicality, but so synchronization, we're now going to do halo swaps by direct copies, but we need to ensure the data is ready beforehand and available afterwards, so that the synchronization MPI win fence. So this very much looks like OpenMP. We do MPI win fence on node when everyone's ready. Instead of doing send receive, I just do a copy, old road of n local plus 1, which is my sorry, I'm writing. So we have a choice here, okay? We can either read halo data or write. I'm going to write the halo data. So I'm going to write the halo data of the guy up the way is my extreme left, and the halo data of the guy down the way is the other thing. So what I should actually put a comment in here. I'm updating the halos through remote writes. I could have done it through, so I'm updating data which is on a different process, which is off the end of my array. Yeah, I'm doing remote writes here. I could have done it through remote reads, but I decided to do remote writes. The off node comms, you have to use send and receive. So you still need MPI calls for internode. So that means in this diagram with the traffic model, the guys at the extreme ends of the node rank 0 and node rank node size -1, they can't do this trick because they have to communicate with different nodes. And so you then have to basically communicate in COM world. You can't just communicate to another node in COM node because by definition that's only you. So you can do MPI send receive with node rank equals 0, node rank equals node size -1. So it is slightly complicated. In a hybrid MPI OpenMP, you have MPI for the communications and OpenMP for the local work. In this model, certain processes in certain phases they're communicating through direct reads and writes, which is a bit analogous to the parallel region in OpenMP, and other places they're doing sends and receives. So the conclusion is, this is a relatively simple syntax for shared memory in MPI. It's much better than a roll your own solution, but I mean, much better than using lower level operating system calls such as shared memory. The possible use cases are on-node communication without needing MPI, and that's the example I have in the traffic model. It's just there to illustrate it. I don't expect it would actually go any faster. But one copy of static data per node, not per process, is where it really comes into its advantage. And the reason I think this, definitely for the second case, the reason why it's much better than hybrid MPI OpenMP is an incremental plug and play. You can choose to only do this for certain routines. You don't have to do it for all the routines like you do for So for hybrid MPI OpenMP, you have to put OpenMP into all your computationally intensive routines. In this model, you can decide routine by routine, are you going to use point-to-point MPI or read and write to a shared array? The disadvantages are you don't have the automatic support splitting up parallel loops. You don't have the scheduling characteristics for OpenMP. And it's a slight technicality, but this array is a bit difficult. If I retain the halos on my local array, which is the natural thing to do, I have to be careful. This is halo data, halo data, halo data, real. The global array is kind of polluted with halo data. It makes the bookkeeping a bit harder. So I think but I think where this comes into its own is the one copy of static data per node, not per process. In about half a dozen lines of MPI code, you can achieve that in a performant and portable way using pure MPI, not having to use hybrid MPI OpenMP. So if there aren't any questions, I will just briefly outline the exercise. There are solutions which you can look at, but I will just outline the exercises if I can find them. Sorry, again, I said my machine shut down, so it's actually I've lost the exercises, so give me a second. Maybe 2 seconds. very slow today sharing. Okay, fine. So now we have exercises. So I have solutions here, traffic RMA.tar, which you can look at if you want. But this is the exercise sheet. And what I would say is effectively implemented a into shared memory or Windows the program on a single node using reads and writes to shared arrays. Okay. If you're a Fortran programmer, there is a subtlety here, which MPI when allocate shared gives you back a pointer. Fortran doesn't understand pointers. In Fortran, arrays are proper arrays, not pointers. So you have to do something a bit weird called CF pointer. You have to basically declare the array as being an allocatable, a pointer array, a shared array, and you basically have to call this thing. This says take the base pointer and make it into a proper array, a proper Fortran array of size n. So that's just a bit of, I just put this in. It's because the when allocate shared gives you back a pointer, but Fortran 90 at least doesn't understand pointers. It wants proper arrays, and this routine from the ISO C binding module converts a C pointer into a proper Fortran array in a portable way. Okay. So that is really all I had to say today. I just wanted to check. I've given you. Yeah, so I have given you. Yeah. So there is a solution called traffic sm.c which uses shared memory to do the local. Yeah, to do the local updates. Yeah, that's correct. And so that there is a full solution there. Yeah, fine. So that was really all I had to say. I hope you found that useful. I am around until 4:45 to answer questions. Your account on ARCHER2 will last for at least another month or so you can carry on doing this, looking at the exercises. Feel free to get back in contact if you want any individual questions. As I said, I'm happy to answer any individual questions you had. So yeah, so thanks for attending, and so I'm happy to take any questions either now or later, or do a screen share on any topic you want. I'll stop recording.